now know that complex organics are everywhere in the solar system. They're found in meteoroids, comets, asteroids, and also planetary satellites. And these organics are nothing to do with terrestrial organic matter, because we have now almost 100 amino acids, where on Earth we're only using 20, and there are unusual nuclear bases, more than the 5 that we have on Earth. And the amount of complexity is quite large. I mean, almost all biological molecules are found in the soluble component of meteoroids, and the insoluble component consists of a very large mixture of aromatic and aliphatic compounds. And we also know that these organics are not made by biological means. They are not breakdown products of life, but they were built up from small molecules to more and more larger molecules. Now, the main question is that are these molecules formed in the solar system, or they could have an extrasolar system origin? So today I want to talk about the only place that we know that complex organics are being made, which is in the late stages of stellar evolution. So after the nucleosynthesis of the element carbon, you stretch up to the surface, and in the stellar atmosphere, you form C2, C3, Cn. These stars, called asymptotic giant branch stars, they have very strong stellar wind. In the stellar winds, you can see now over 80 different kinds of molecules, and after that is the stage called planetary nebulae, which lasts about 20,000 years. So we can detect by both infrared and microwave means that the rotational and vibrational lines of over 80 different kinds of molecules in the stellar winds, which consist of chains or rings and other kinds of organic molecules. So the AGB stars are very prolific molecular factories, but the most interesting come in the planetary nebula phase, where it was first detected in the late 1970s of the so-called unidentified infrared emission bands at 3.3, 6.2, 7.7, 8.6, 11.3 microns. And they were pointed out almost immediately that the 3.3 micron feature is due to the stretching mode of aromatic compounds. Now, these UIE bands are now seen in galaxies as far as 10 billion light years away, so we know that complex organics are already present in the early universe. Okay, now, and also there are a lot of them, because up to 20% of the total light output from those galaxies come in the form of these UIE emissions. Now, these are very interesting because we know that they are first seen in the planetary nebulae, but not seen in the asymptotic giant branch star, so the first synthesis must have occurred in between the end of the asymptotic giant branch to the first formation of planetary nebulae, which is a very short time. So we have from the stellar wind, we have a dynamical age of about 10,000 years, and the age of planetary nebulae is about 20,000 years. So we know that whatever synthesis occur must be in the 1,000-year lifetime. But of course, the most interesting would be to discover objects in between these two stages to see whether there are any sign of organic synthesis. Okay, so Bruce Wifneck and I were able to discover about 30 transition objects, and these are all the objects that some examples of the protoplanetary nebulae that we discover. After the discovery, the first thing we do some spectroscopic follow-up. We find that they have aliphatic transitions at, for example, C stretch of either symmetric or antisymmetric methyl and methylene groups. And the 11.3 micron feature, although usually due to our plane bending modes or aromatic compounds, but there are other bands which suggest that these rings are very small. The most interestingly, there are broad emission features around 8 and 12 micron, and we suggested because many aliphatic compounds have in-plane bending modes around 8 micron, and our plane bending modes around 12 micron. So these two plateau features could be due to a superposition of aliphatic compounds of different sizes and strengths. So to summarize, we have a phenomenon which has a set of strong features, and also which some of them could be due to aromatic compounds, and there are also aliphatic compounds, but there are also broad features which are about 2 microns wide, which are probably due to supercomposition of different plane and in-plane bending modes. So the key question is that what is the chemical structure of this carrier? So in the last 30 years, the most popular hypothesis is the polycyclic aromatic hydrocarbon hypothesis, which says that if you have 50 carbon ring molecule, that they will be excited by UV radiation. In the cascade down, they will go through these infrared vibrations and give you these UIE bands. But these hypotheses have a lot of problems. I mean, the most obvious one is that these are simple molecules, the lines are narrow, and they are primarily excited by UV. They have very little absorption in the visible, but we now know that the UIE bands are seen in refraction nebulae, in polar planetary nebulae, so they are definitely excited by lower energy photons. And also, if the UIE bands are due to pH molecules, they would have very strong electronic transitions, but the detection limit is 3 orders of magnitude lower than what was predicted. Now, the chemists are very unhappy about this hypothesis because pH molecules are very simple molecules and their properties are well known. So there are a lot of literature about that the lines that were detected astronomically have really nothing to do with the pH molecules. Now, however, to fit, if you look at the literature, astronomical literature, you see beautiful fit to the UIE bands. How do they do it? They use a mixture of pH molecules of different sizes, structures, shapes, ionization states in order to create a fit which is resemble the astronomical spectra. The Ames group are very kind to allow us to have access to the database and also their fitting routines. So in the papers published in the Astrophysical Journal, we're able to show that their routine are able to fit almost anything. So it's really not very useful because they have so many free parameters in the fitting process. Now, if they are not pH molecules, then what is? Now, if you mix 2 elements, hydrogen and carbon, together, they can create amorphous forms of a variety of structures. So pH molecule is just the line in the bottom. So in one corner, we have graphite, which is pure aromatic, and then we have pure aliphatic, which is like diamond. But really, anything in the middle is possible. So in 2011, we proposed a model that these are due to mixed aromatic, aliphatic, organic nanoparticles, and which has small rings, but these rings are linked by aliphatic chains of different sizes and different orientations. And they also have impurities like oxygen, nitrogen, sulfur, and so on. So they are not 2-dimensional, but 3-dimensional, and they are not simple planar structures or fixed structures, but amorphous. Okay, so this is an example of 169 carbon MAON molecules, and you can get an idea of the schematics of this kind of structure. So they are disorganized. Okay, so the last several years we published a number of papers on the properties of these MAON molecules and how they may be related to the observed UIE structure. I won't be able to go into the details here, but just to let you know that the way we do it is we start with simple pH molecules so that we know what we are talking about, and we attach aliphatic chains to the structure by gradually adding more complexity. Then we can hopefully understand where the vibrational modes are. So we just show some examples here that now with the present quantum chemistry techniques, it's really possible to do these kind of calculations, because the chemists never did that, because to the chemists, as soon as they understand the principle of vibrations, they are already happy. But for us, that if we want to compare the astronomical spectrum with molecules, we have to look at more complex structures and see what kind of modes are there. And in the process, we discover that, for example, there are some couple modes, and which are or some more complex vibrational modes, which are not being studied in the literature. Okay, so I'm here just showing some examples to say that these kind of calculations are possible. So the interesting thing is that if stars near the end of their lives are able to make very complex organics, because they can make it over a very short period of time, over hundreds or even thousands of years. And we know that through the stellar wind, they can be ejected all the way through the solar system, through the Milky Way galaxy, across the interstellar medium. So it's quite possible that some of those complex organics would be injected into our primordial solar system. So there's some evidence of it. You see, for example, in the case of the pre-solar grains, we now know that we can hold in our hands products of minerals which were ejected, created by asymptotic giant branch stars because of the isotopic ratios. So whether the kind of organics that we see in Titan or in comets or meteoroids have anything to do with stellar organics is something that we should explore more in the future. So first I want to point out that organic compounds are everywhere in the universe. So we have a lot of organics in the solar system. They're in stars, they're in the stellar clouds, they're in the diffuse interstellar medium. By looking at absorption line studies, we know that 50% at least of the carbon in the diffuse interstellar medium are in the form of aliphatics. And a detection of the UIE bands with galaxies at highest redshift of 2, suggesting in the very early stage of the universe, we already have complex organics. So these organics, are consistent with the carrier being complex molecules with amorphous structure, with mixed aromatic aliphatic structure. And I want to emphasize that the only objects that we can actually see these organics being made are in the protoplanetary nebulae and planetary nebulae, where they have a dynamical age or evolutionary age of only thousands of years. So this places a very strong constraint on what kind of chemical network that we have available to form these organics. And these are not exotic objects, because over 95% of all stars in our own galaxy go through the planetary nebula phase. So these are ordinary stars. Every star will go through this phase of making organics over a short period of time. So we know that AGB star ejector can survive the journey through the interstellar medium all the way to the solar system and to the Earth. So it's not impossible that some of the macroorganics that we have now in the solar system may find their heritage in stars. So I just want to leave to you some of the papers, so the more technical aspects, those will be cited in some of these papers. Yeah, thank you.